Imagine the quest for, the holy grail in robotics. Building truly intelligent, adaptable robots that can do complex, nuanced tasks, not just in some perfect lab setting, but out there in the messy, unpredictable real world.
Right.
We're talking about robots making your sandwich, carefully pouring tea, maybe handling dynamic stuff on a conveyor belt, or even folding laundry. How close are we, really?
Yeah, that's the big question.
Well, today we're taking a deep dive into Genie and Visionner. It's this groundbreaking new unified world foundation platform for robotic manipulation. Comes from the Agibot Genie team, NUSLV Lab, and BUAA.
It's really fascinating stuff.
It really is. A look at how researchers are kind of collapsing these traditionally separate stages of robot development into just one single cohesive system.
And hey, for those of you who need the quick version, the 1-minute summary, the core problem, the biggest bottleneck in robotics today, is fragmentation. You've got these separate, totally disconnected phases for gathering data, then training models, then evaluating. It's just slow.
Painfully slow.
Exactly. So Genie Envisioner, or GE, it smashes that paradigm. It unifies all these stages into a single, powerful, video-generative world model. It's built on 3 main pillars. First, there's GE Base. That's the foundation of the world model that predicts how things interact. Then GE Act, the action model that turns understanding into precise robot movements. And third, GE Sim. This is a super high fidelity video-based simulator. It lets you do lightning fast policy development and testing.
Okay.
So this unified system, it allows for truly general purpose manipulation, really impressive adaptability to new robot hardware with minimal effort, and it just radically speeds up the whole development cycle. We're moving beyond those old siloed ways.
Sounds incredibly ambitious.
It is, and we'll unpack exactly how it pulls off these impressive real-world results and, crucially, how its evaluation framework actually confirms its progress.
Okay, let's definitely unpack that. Before we dive into the specifics of Genie and Visionner, what exactly is the fundamental challenge here, the one they're trying to solve in robotic manipulation? Because, we see cool demos all the time, but building genuinely versatile robots still feels incredibly hard. Why is that?
Yeah. It's a critical question. It really cuts to the chase. The problem GE is tackling, even with all the progress we've made, robot development often feels like this disconnected piecemeal thing.
Right.
Imagine trying to build a house where the foundation crew, the framers, the electricians, they all use completely different plans and tools and don't really talk to each other. That's kind of what robotics often looks like now.
Well, okay, like a patchwork.
A patchwork, exactly. Isolated data collection, separate training pipelines, different evaluation setups.
So a lot of bespoke, disconnected bits for each step.
Precisely.
Yeah.
Historically, each stage needed its own specialized infrastructure. Painstaking manual data curation, task-specific tuning every single time. And this fragmentation, it has real consequences. It massively slows down how fast you can iterate. It makes it incredibly difficult to figure out why a robot failed.
Yeah, the debugging nightmare.
Totally, and it hinders reproducibility, makes it hard to scale things up.
Yeah.
So the core bottleneck really is the lack of an integrated framework. Something that can learn and evaluate manipulation policies in a unified end-to-end way.
Okay.
That's the gap Genie and Visionner is built to fill, bringing it all under one roof with this single video-generative world model.
Right. So if that's let's say, the chaotic landscape now, how does Genie and Visionner step in with its unified platform? Let's start at the core, GE Base. How does this foundational model even begin to understand the world?
Yeah, GE Base is where the magic starts, really. And what's groundbreaking is that it's a large-scale, instruction-conditioned video diffusion model.
Okay, video diffusion, like generating realistic video.
Exactly, but specifically trained on robot interactions. Its main job is to capture the spatial dynamics, the temporal flow, and the semantic meaning of real-world robotic actions, all within this structured, latent space.
Latent space. So it's internal representation, it's understanding.
Pretty much. It's deep internal model of how the physical world works, what objects are, how they move, and crucially, how all that connects to language instructions, like pick up the red block.
And it learns this from just a ton of data, I gather.
Oh yeah, absolutely.
Yeah.
We're talking about training on roughly 3,000 hours of video-language paired data. That spans over 1 million real-world robotic manipulation episodes.
Whoa.
Pulled from the Agibot World Beta dataset.
Yeah.
It's a staggering amount of practical, real-world experience for an AI.
So how does it, generate the video?
Architecturally, it generates video chunks auto-regressively. So it predicts the next bit of video based on what it's seeing now, the language instruction it got, and this thing called a sparse memory mechanism.
Sparse memory, for remembering things long-term.
Exactly. Key for tasks where the robot needs context from, a few steps ago. And what's really clever is how it handles multiple viewpoints. It's not just one camera.
Ah, right. You mentioned multi-view.
Yeah, it integrates input from a head-mounted camera and 2 wrist-mounted cameras. This gives it a much richer, more embodied sense of the scene and its own arms within it.
That's a much more complete picture than just one overhead view. Beyond just the sheer volume of data, was there anything special about how GE Base was trained to, digest all that complexity?
Yes, absolutely. The training strategy is pretty sophisticated. It involves a 2-stage pre-training process. First stage is multi-resolution temporal adaptation.
Okay.
So here they sample video frames at different rates, from 3 Hz up to 30 Hz. This basically teaches the model to understand motion regardless of how fast it's happening, or even if frames get dropped. It builds this robust sense of movement.
Makes sense. And the second stage?
Second stage is low-frequency policy alignment. Here, they fine-tune it at a fixed 5 Hz. This step is really about efficiency and getting the video model's timing aligned with what the downstream action policy will need.
Got it. Aligning the seeing part with the doing part.
Precisely. This whole rigorous pre-training process allows GE Base to build this strong map from language instructions straight into this embodied visual space, capturing those essential dynamics of robot manipulation.
Okay, so GE Base builds this really comprehensive, multi-view understanding of the world, and it's tied to language. So the natural next question is, how does that deep understanding then translate into a robot actually doing stuff? Into precise physical movements? How does Genie Envisioner empower robots to, act?
Right, this is where GEX steps in. And it's designed as a lightweight, parallel, flow-matching action model. Despite being relatively small, about 160 million parameters, it's incredibly efficient.
160M, that's actually quite lean for these kinds of models nowadays.
It is, yeah. And its core job is to map those latent representations from GE Base directly to executable action trajectories. So basically, it takes that deep visual understanding, combines it with the language instruction, and then spits out the exact sequence of joint movements or torques the robot needs.
Okay.
And this allows for really precise, generalizable control across different robot bodies, importantly, with minimal supervision.
Minimal supervision. That sounds like a huge deal for actually deploying robots. What kind of performance are we talking? Is it fast enough for real time?
Surprisingly fast, yeah.
Yeah.
GE Act gets low latency end-to-end control. It can generate these complex, 54-step torque trajectories in just 200 milliseconds.
Wow, on standard hardware.
On a commodity GPU, yeah, like an NVIDIA RTX 4090. So
Yeah.
that's definitely real-time performance, which you absolutely need for dynamic tasks.
Absolutely.
And its generalization abilities are, frankly, quite impressive. On its home turf, the Agilbot G1 platform, it nails a whole range of complex tasks. Things like make a sandwich, pour a cup of tea, clean the table, heat food in the microwave, even dynamic stuff like pack laundry detergent from a conveyor.
These aren't just simple pick-and-place tasks, then.
Yeah, definitely not.
I do.
They involve handling squishy things, deformable objects, pouring liquids accurately, sometimes needing memory for sequential steps. Really quite complex.
And the cross-embodiment part, adapting to totally different robots, that seems like the real acid test for general-purpose AI.
Totally. And this is where it gets really exciting for cross-embodiment generalization. It adapts successfully to completely new systems, like the Agilex Cobot Magic, doing things like box folding, cloth folding, or even a dual Franca setup.
Okay.
And here's the kicker. It only needs about 1 hour of teleoperated demos for post-training on these new robots.
Just 1 hour? Seriously?
Yeah, think about that. Just an hour of human guidance to get it working well on totally different hardware. This minimal data approach lets it significantly outperform existing baselines like UniVLA, GR00T0.
Even if those baselines had way more training data on that specific robot.
Exactly. Even when those other models had extensive pre-training specifically for their own embodiments, that's a massive leap in efficiency for getting robots out there doing useful stuff.
That is a huge step forward for real-world deployment. I also saw something about a slow-fast asynchronous inference mode. How does that help?
Yes, that's a clever trick for computational efficiency. Basically, the system runs the seeing part and the doing part at different speeds.
Okay.
So the video model, GE Base, runs slower, maybe at 5 Hz, generating sparser visual predictions. But the action model, GE Act, runs much faster, say at 30 hertz, churning out those dense action commands.
So it thinks visually a bit slower but acts really fast.
You got it. It lets the system be efficient with visual processing while still having that high-frequency control needed for smooth, precise movements. Best of both worlds, really. Efficient prediction, agile control.
Makes sense. Now, beyond just controlling robots, Genie Envisioner also has this simulation piece, GE-Sim. How does that fit into the unified platform? How does it speed things up?
Yeah, GE-Sim, the Action Conditioned Neural Simulator. It's a real accelerator for development. Its main advantage is generating these super high-fidelity rollouts for closed-loop policy development.
High-fidelity rollouts, meaning realistic simulations of what the robot would do.
Exactly. And it does it incredibly fast. We're talking thousands of simulated episodes per hour if you run it on a distributed cluster. This just massively speeds up testing and training robot policies. Cuts down hugely on the time and real-world costs you'd normally spend experimenting.
So it's like a super fast virtual test track for robot policies, and it learns directly from real videos.
That's a great way to put it. It works by basically taking GE Base's video generation smarts and repurposing its learned dynamics into a simulator. This enables what's called closed-loop evaluation.
Right. Policy acts, simulator shows the result, policy uses that result for the next action.
Exactly. That whole loop happens inside the simulation. Technically, it uses this hierarchical action conditioning mechanism. It integrates specific robot pose info, things like pose-to-image conditioning, that projects the robot's predicted hand position and orientation right into the pixels of the generated video, making it visually accurate. And motion vector conditioning, which encodes how the pose changes over time, the temporal dynamics.
So it's not just making a plausible video, it's making a video that accurately shows the robot's intended movements and what happens because of them.
Precisely. And that's why it's such a compelling alternative to traditional physics simulators. Those usually require engineers to painstakingly model every single object, every material, every interaction.
Yeah, tons of manual work, and often struggles with real-world messiness like cloth or liquids.
Right. GE-Sim learns those dynamics directly from real video, so get high visual fidelity, way lower deployment costs, and this scalable, flexible simulation without all that painful manual environment building. It's just much more practical for iterating quickly.
Okay, so we have the world model, the action model, this powerful simulator. It all sounds incredibly impressive. But what does it all mean? How do we actually know if Genie Envisioner is really pushing the field forward? What's the compass for this new territory?
That brings us neatly to EWMBench. This is a standardized benchmark suite they developed specifically for embodied world models like GE.
Okay, a specific benchmark. Why not just use standard video metrics?
Because standard video metrics, they're okay for YouTube videos, but they aren't strict enough for robotics. Robot manipulation has these really specific structural constraints, like the background shouldn't randomly change, the robot's own body should look consistent.
Right, only the parts that are supposed to move should move.
Exactly. Only the robot's actions and how they affect objects should evolve realistically. EWMBench was built from the ground up to measure that, with metrics tailored for these unique requirements.
That makes total sense. So what are some of the key things EWMBench actually measures?
It looks at several crucial aspects. First, scene consistency. It uses DynoV2, a vision model, to check if the background and static parts of the scene stay stable. No weird flickering or disappearing objects allowed.
Good.
Second, action trajectories quality. This measures how well the simulated robot movements match up with the real ground truth. It breaks this down further into spatial alignment, comparing trajectory shapes.
Did it follow the right path?
Yeah. Temporal alignment, using things like dynamic time warping to check the timing. And dynamic consistency, looking at velocity and acceleration profiles using Wasserstein distance to see if the motion itself looks physically realistic.
So not just what the robot did, but how it did it, and if the motion makes sense over time.
It's exactly right. Third, motion semantics. This gets at whether the model understands the task. It checks semantic consistency globally, using BLEU scores on video summaries, and also step-by-step using CLIP similarity. Did it do the right things in the right order?
Okay.
And crucially, it also checks logical correctness. They actually use another AI, a vision language model trained on GPT-defined error types, to spot things like hallucinated actions, the robot doing something impossible, or objects just vanishing into thin air.
Wow, using AI to check the AI's logic. That's clever.
It's pretty robust, yeah.
Yeah.
It penalizes those logical violations. And finally, semantic diversity. Does the model produce varied but still valid ways of doing the task? Or does it just repeat the same thing over and over? Uses CLIP embeddings to check that.
Very thorough. And the results, how did Genie and Visionner actually do on EWMBench?
The results are really strong. GE-based consistently beat the baseline models across multiple dimensions, especially in things like temporal alignment and dynamic consistency. That suggests it has much stronger control-aware generation fidelity.
Meaning it generates video that's more useful for actual robot control and simulation.
Precisely. And what's really convincing is that the EWMBench rankings line up really well with human judgments. So when the benchmark says a model is good, humans watching the videos tend to agree. That makes it a pretty reliable tool for the whole field.
Okay, so from this unified platform to a really robust, tailored evaluation framework, Genie and Visionner is clearly pushing boundaries. What's the bigger picture here? For, instruction-driven, general-purpose embodied AI, where does this take us?
Well, I think this work really does establish a scalable, practical foundation for that goal. Instruction-driven, general-purpose embodied intelligence. It feels like a significant leap towards robots that can genuinely understand and carry out complex human instructions in all sorts of environments.
And they're open sourcing it too, right?
Yes. Huge benefit for the research community. They plan to release all the code, the pre-trained models, the whole EWMBench suite when it's published. That should really help accelerate future research. It's vital for progress in a field moving this fast.
That's fantastic for open science. But, no system's perfect. I know the paper talks honestly about limitations. What are some of those key areas needing more work?
Yeah, and that transparency is important, right? First, there's data coverage and source diversity. The AgiBot World Beta dataset is big, but it's mostly from one robot platform. They know they need to bring in more diverse data, maybe from the internet, maybe more simulation to get better generalization, especially in new situations or low data scenarios.
Makes sense. More variety in, more variety out.
Exactly. Second, embodiment scope and dexterity. Right now, it's focused on upper body manipulation on tabletops, using simple parallel jaw grippers. To get truly general-purpose robots, you need to handle dexterous tasks with multi-fingered hands and whole-body movement locomotion.
Right, walking, climbing stairs, fine manipulation.
All that jazz. And finally, evaluation methodology. EWMBench is great, a big step forward, but it still relies partly on proxy metrics and some human checking. Getting fully automated, super reliable assessment of whether a task really succeeded, especially spotting subtle failures, that's still an open challenge, needs more research.
So, still work to do, for sure. But it definitely sounds like Genie and Visionner marks a major milestone, kind of setting a new standard for how we think about building intelligent robots.
Absolutely. Despite those limitations, it feels like a really meaningful, critical step towards that vision of Genie-embodied AI systems that might eventually reach AGI-level manipulation skills. It provides a solid blueprint for the next wave of intelligent, versatile robots.
So we've really seen how Genie and Visionner is, masterfully bringing together these worlds that used to be separate: learning, simulation, execution, all into one powerful video-generative framework.
Yeah, it's quite an integration feat.
And our discussion really highlighted its, remarkable knack for complex tasks, generalizing to new robots with barely any new data, and being tested by a benchmark that actually gets what matters for robot performance. What's the big takeaway for you from this deep dive?
Given this big step towards unified world models and these really versatile robots, it makes you wonder, how might the role of humans, specifically human teleoperation, evolve in training robots? Are we heading towards a future where robots learn complex stuff mainly by simulating endless possibilities in these super rich world models, needing less and less direct human demoing in the real world, maybe shifting our role from being direct teachers to more like high-level curriculum designers for AI?